Well, I hope you were able to successfully figure out all of these different answers here on your ionic bonding crisscross method, and they were available with the sub. You can take a look there and see, and we'll go over these next time I'm in class with you as well. So we're going to continue on now with the next type of bonding, and we'll revisit this and work together. So in your notebooks, and you might be mad at me because I keep making assignment number 4 get bigger and bigger. We just finished up our notes out here on ionic bonding, about electrons being given by metals, taken by nonmetals, when they join together in perfect ratios so that all the negative charges perfectly balance the positive charges. That's what we did the crisscross with. We get a stable compound. It will know what the compound formula is. In this case, we said that it took 1 beryllium with charge to perfectly balance. It needs 2 fluorines with the -1. And we call this beryllium fluoride. So maybe I should write that. Beryllium fluoride, F-L-U-O-I-D-E, beryllium fluoride. So now we're going to go on to, this was ionic bonds, this was part A. We're going to now do part B under types of bonding. Now look it, I know if you ran out of pages, you know what, just go to the next blank page and you can write assignment number 4 continued, or you can do what I've been doing in my notebook. I just slide in another page that I'll tape onto here, but do whatever is going to be best for you. So this is going to be covalent bonds, part B. So I'm going to do it on a fresh piece of paper here, which I'm going to then tape into here. Hey, okay, if you're mad with this, here's some chemistry for you, okay? Be nice, okay? We're all doing our best, or you can do it this way. You can have beryllium, nitrogen, iodine, and cerium, or beryllium, nickel, and cerium. Anyway, so just be nice. We're all doing our best job. So we are going to be on, this is still assignment number 4. It's going to be part B. We had ionic bonding was part A, so now we're going to do part B. So I'm going to put a B here, and it's going to be covalent bonding. So cooperative, valent, the outer electrons in the shell, covalent bonds. Draw a line here so we have a review section on here. Now, once again, with covalent bonding, we've already learned a couple definitions. When you've got nonmetals bonding to nonmetals, nonmetal to nonmetal. That's one definition. And then as we're going to see, the other that I had you do in starters last week and we began with is that over here when nonmetals bond to each other, they share electrons in pairs. They share pairs of electrons. And that's going to be, that kind of distinguishes them from the metallic bonds when we get into that. So let's just get right into this. Let's draw a diagram and let me see. Oh, wait a minute. I was looking for a pencil earlier and there was one right in front of me. So let's draw a really simple Bohr model for hydrogen. We're not going to bother to put protons or neutrons. We'll just put H right here. We'll just put the nucleus around it. And hydrogen is in period 1, so it only has 1 shell. And it only has 1 electron. It's in group 1, that's why it only has 1 electron. I'll just put its 1 electron right there. And now we're going to draw another hydrogen over here. So because we're talking about a couple of hydrogens coming together. Now I'm going to color code the electrons. You don't have to. I'm just going to do it just so that it's a little bit easier to kind of possibly see. So this hydrogen's got that 1 electron. Both of these atoms by themselves, they are unstable. They are not happy. they want to have a full outer shell of electrons. Now, we call that the octet rule. They want to have 8 electrons. There are a few exceptions. Helium, hydrogen, these elements are so small, they only need 2 electrons. So hydrogen wants to have 2 electrons to have its first shell totally full, but it's not, and it's got to live with disappointment. Helium is laughing like crazy. It's got its 2 electrons in there, and it's really having fun. So what hydrogens do, if they come together with each other, they can bond together, and they can form what kind of makes them look like they're sort of like a helium. They think they'll be a noble gas. So we're going to draw these coming over here, and we'll have their orbitals kind of overlap a little bit. So let's see, this one, there's the one I drew in dark from this atom, and this electron right here. So now what happens is, when they get close together to each other, they have a pair of electrons that they're sharing. Now what happens, they become happy. We call it stable. Now hydrogen, it's easy to break the bonds there. Hydrogen's a great fuel. They use it as rocket fuel quite a bit, and it can be used as a fuel. But they're relatively stable, and they're really happy with each other. But the drawback is they became stable. They kind of think they're a helium molecule now, but they got to stick together. And they will until something comes along to separate them out. So what we've got here, we've got one pair of electrons being shared. So let's just, one pair of shared electrons. Can you see that? Make sure, one pair of shared electrons. Because we said they share in pairs. Now we're going to do an example of where they're sharing more than just one pair. So let's get our friend oxygen. So again, we'll just do a modified Bohr model. We'll just draw O for oxygen. We're just going to draw, okay, and we're going to draw its, we'll do that. So there's its nucleus, and we're just going to draw its valence shell, okay? So oxygen is in group 6A, or group 16 on the newer periodic tables. It has 6 valence electrons. Has 6 valence electrons. So what I'm going to do is I'm going to draw, let's see, 1, 2, 3, 4, 5, 6 electrons there. Oh wait, did I do that right? Yeah, okay, I think I got that right. And then we're going to draw another oxygen over here. It's got 1, 2, 3, 4, 5, 6 electrons. We'll put the symbol for oxygen. There's its nucleus. We're just drawing the valence. I should have drawn that as a dotted line to be consistent. So what's going to, oh, and I guess I should, I'm going to color code these guys. Now both of these atoms right here, they're unstable, okay? Oxygen needs 2 more electrons to satisfy the octet rule. Now if they can join together over here, what can happen is they can get some bonding, they can share these, and so let's draw this again. I'm going to draw these overlapped. This is their valence electrons, the valence shells here. And so I'm going to draw, let's draw the O in the middle. So we got that. And let's draw, okay, now this so this guy right here, I'm going to go ahead and put him right there. And then we got these two hanging out there. And this one, this pair right here, I'll put one of them there and another one over here. So so far we've got 1, 2, 3, 4, 5, 6. We haven't violated anything. Now let's draw in the 6 electrons of this one. So I'm going to put that electron, I'm going to put it right over here. I'm going to put that electron right over here. And then that one here, this one there, and there. So now, if we take a look, we've got 1, 2, 3, 4, 5, 6 of the electrons from this one. But look how they overlap. So now, this one has 6 electrons, but it's also got these 2 electrons in its outer shell. So as these electrons are spinning for a million, billion, trillionth of a second, this oxygen has 8 electrons in its outer shell. In the next million, billion, trillionth of a second, this one takes them, and this one's got 8 electrons in its shell. So by doing that, they can become a stable compound. That compound is very happy. It's stable now. It's got 8 electrons. Now, we can interact. I mean, oxygen is part of what you need to have a flame. and fire. So yeah, it can react, but it's relatively stable, and they're kind of happy until we add some more energy to it. And what we've got is, now we've got 2 pairs of shared electrons. Now I'm going to kind of come up and show you what we're going to start to see now. I'm going to back up to over here. Hydrogen, we could write this bond like this. We could say hydrogen, there's 2 dots to represent the electrons. Or we could do this. Chemists sometimes will do this. They'll use a line to represent that they're sharing a pair of electrons. Chemists tend to be really lazy. A lot of times they'll just do this. They won't even bother to draw the little dots. They'll just go like this, H-H. That dash means that is a pair of electrons. So over here for oxygen, we could do oxygen and put 8 electrons all around here. Oh, that would be a mess. So what chemists do, they're just going to say, wait a minute, we've got 2 pairs of electrons. Let's just do this. We can go like this. Okay, then there's what? After these pairs, we have what, 4 others. So they might do 1, 2, 3, 4, 1, 2, 3, 4. They could do this, but chemists are lazy. So if they're going to draw what we call the structural formula, they're just going to go like this, just straight lines, and each of those lines means 2 electrons, 2 pairs of there's a pair of electrons here and there. So now we got O2. Oh, by the way, yeah, so we can call this hydrogen 2, 2 hydrogens. This is O2, which we breathe to go on, to carry on life functions. Oxygen's really cool because it reacts with other stuff and it can pull electrons off, which kind of drives our metabolism. Okay, one more, and then we're done with this. So we're going to do carbon and oxygen. So let's do the element carbon now. So on the periodic table, carbon is in group 4A, or the newer group 14. So it has 4 valence electrons. So I'm going to draw just its modified simple Lewis structure. There's C for carbon. There's the nucleus. And carbon has 4 electrons. So I'm going to put these electrons like this over here. Obviously, I'm setting this up so it's easy to bond them together. Then we're going to bring in our friend oxygen. So I'm going to draw oxygen just in red this time. You don't have to worry about it. We got oxygen there. Here's its shell, and it's got 1, 2, 3, 4, 5, 6 electrons. And we're going to get another oxygen. So there's its nucleus. And oxygen has 6 electrons in its valence shell. We're just talking the outer shell because we don't really care about the inner shells that are stable. We care about those outer valence shells. Oxygen is in group 6A, or the new group 16. So it's got 1, 2, 3, 4, 5, 6. We're going to actually learn there's a way to even draw those later. So these are all unstable. They are not happy. They want to have it all too. They want to have 8 electrons. So they will join together. So now when we redraw this one, here's carbon. There's its 4 electrons. Like that. And now let's draw oxygen right next to it here. We'll draw its shell right there. Oh, I should have had that slightly overlapping, but okay, so now I'm going to take, once again, this electron right there. I'm going to put it really close. In fact, I'm going to kind of make my line go like that. There we go. So like that. And then this electron I'm going to put right there. Then we've got this one and this one, and we got 2 more. Now let me make sure. This oxygen has 1, 2, 3, 4, 5, 6 electrons. It's going to be kind of sharing that one. Maybe I should make this kind of overlap a little more. Well, we'll get the hang of it here. And then I'm going to make this one definitely overlap. Okay, in fact, I'm going to work backwards. I'm going to take that one, put there, and this one and put there. 1, 2, 3, 4, 5, 6 electrons. Call this one carbon. Oh, I know, that was oxygen, my mistake, oxygen. So now what we've got, I know it's kind of clunky here, but let me cover up these oxygens for a moment. For a million billionth of a second, this carbon has 4 red electrons, 4 of its own electrons, for a total of 8 electrons in its valence shell. For the next fraction of a moment, this oxygen is sharing those 2 electrons, so it has 8 electrons. And for the next fraction of a moment, this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons there. So we end up with carbon, and we got 2 sets of electrons here that are sharing between that oxygen, and we've got a pair of electrons that are being shared there. And then chemists will just tend to say, well, if we're going to draw the structural formula, we're just going to do this. They don't even want to bother to draw the dots. That lets them know that there's what we call a double bond. 2 pairs of electrons being shared here and here, and another 2 pairs there and there. This is our friend carbon, 1 carbon, and 2 oxygen, CO2. So, this is how atoms can share electrons. But something happens in nature. They don't always share. They don't always share their electrons equally. They don't always share their electrons equally. And so we're going to do a little, you're going to have a reading passage now, and what we're going to talk about is I want you to imagine that you've got a polar bear and a penguin, and they're trying to share something. So in this case, in this analogy here for this, we've got a polar bear and a penguin, and they're sharing an ice cream cone. And which one of those two, now they are sharing, but which one of those do you think is going to get more of that ice cream cone, huh? So at this point, you're going to be reading this graphic novel, which is really a novelization, an analogy of how atoms can share electrons, but they don't always share equally. Oh, I love this diagram here. Look how they show the polar bears, the nonmetals over here, really big, and then the penguins, which are representing metals, really. Anyway, okay, you don't care, but it's kind of cool because it shows how much they need electrons. But you don't care about that. You're going to read, and then there's some questions you'll get. Okay? So, toodles.